Okay, now I haven't given a rigorous argument here. We're doing an overview. Just my main point here is you've got a couple of laws and everything else follows from these laws. Okay. If you do this integral, you're going to find, at least in this case, that the line integral of b dot ds as you go around this loop is going to equal 4 pi k prime times the enclosed charge. Do that integral, it comes out. And of course, you know, that is, you might like the mu naught notation better. Personally, I always like the notation that doesn't carry a pi in it, because pi's, you know, they get squared, they end up in reciprocals, it's hard to remember where they are. It's hard to relate it. Now, that's just a matter of personal taste. Use whatever works for you. Now, Ampere's law basically says this, except Ampere's law also includes displacement current. And I did describe displacement current in terms of a capacitor. If you have a varying electric field, a varying voltage across a capacitor, just imagine two plates, and there's a current running, transferring charge from one plate to the other. Okay, well, the charge on the plates is varying, and in some ways it's as though you still have a current running between the plates. You don't. The current's going from this plate around here, and there's nothing being transferred between the two plates. Still, it can act that way, especially as regards a magnetic field that can be created by a varying electric field. Without going into a lot of detail, that's what displacement current is all about. And unfortunately, in this course, we had other slightly higher priorities, and we didn't get to talk about displacement current. You can read more about that, and I do recommend that you do. But you'll be encountering it in more advanced courses. Okay. Now that's kind of, you know, the version of Ampere's law where you don't have to worry about displacement current. I did talk a little bit more in class about electric and magnetic fields and an electromagnetic wave, but I'm not going to try to wave my hands in a video over that. You know, look that one up. That was in response to your question, where to use Gauss's law for magnetism. And that's in applications that would be there in the next chapter. Don't have any direct applications in the material that we've covered, so it's not something that you're going to need to use, although you should know it. Okay. Okay, we'll talk here about, you know, Faraday's law, Lenz's law. I always have trouble even seeing that there's a difference. Faraday's law seems to include Lenz's law, but we'll talk about that in a minute.